Hey everyone, how it goes, and welcome back to Computer Science 146. Today, we're going to discuss more binary search trees. In a previous lecture, we started defining what the tree data structure is. And it's simply a data structure that can be defined recursively as a collection of nodes, where each node is a data structure consisting of a value together with a list of references, otherwise known as edges, with the constraints that no reference is duplicated and none points to the root. We then further establish that trees cannot have cycles. After that, we started going over common terms associated with the tree data structure. And some of the most important ones to keep in mind: the root is the topmost node of the tree, and the parent and child relationship. A parent points to a child. In other words, a parent references a child. Then we established a specific kind of tree called the binary search tree. Now, specifically with the binary search tree, the node's data has to be comparable in some way. For each one of the nodes, a binary search tree only has at most two children, a left child and a right child. The relationship between the left child and the parent is the left child's value is always less than the parent's value. The right child's value is always greater than the parent's value, and there are no duplicate values. Also, for our definition, we're going to assume that leaves are the null references. Now, the last time we went over how we can add elements to a binary search tree and how we can traverse through the tree. Now let's focus on its namesake. How do you search in a binary search tree? So first of all, what you do is you just start from the root. And understanding the properties of a binary search tree, that the left child is always less and the right child is always greater than, we can use this to efficiently find a value. So let's say, for example, we were looking for the value 4. If we start from the root value right here and we're searching for 4, well, the thing is, 4 is less than 8. We don't need to check the right-hand side because we know as 4 is less than 8, we only need to check the left-hand side. So as 4 is less than 8, we go left. Now we look, 4 is greater than 2. This indicates that we don't need to look at the left-hand side because all these values are less. We just have to look at the right-hand side. So as 4 is greater than 2, we then go right. And now the target value 4 is equal to the data here 4, and so we return true. Let's see how this looks in code. Now right here we have all the code that we have previously established. We're going to keep adding elements to this linked binary search tree. The first thing that we're going to do is create a public Boolean search for TA data. We're going to do this recursively, so once again, I'm going to separate out this callable method that's going to call the recursive method. So private Boolean search. In this version of search, we need to pass in node a node and T a data. Now from the public search, we're going to return search starting from the root looking for a data. Now inside of here, we do have to worry about a couple of the halting conditions. So if we pass in a node and it is a leaf, so its reference is null, that means we have searched through this whole tree and didn't find the value, so we must return false. Now, if this node is not null, then we need to compare this data versus the node's data. So for instance, else if the data that we're searching for dot compare to, if this data is less than the node's data, this means the target value that we're looking for was less than this value. So this means we have to go left. So then we recursively call search, starting from a node's left child, still searching for the data. Now once again, the compare to method does not return a Boolean value. What this returns is an integer value. So if this data compared with this data was less than 0, this indicates that this data was less than that data. Now alternatively, else if a data.compare to a node.data, and this time it's strictly greater than. Now this indicates that this data was greater than that data. We must then go right. So we return search a node.rightChild and a data. Now finally, if the data we were comparing to was not less than, the data that we were comparing to was not greater than, then we know they are equal. And so we can sufficiently return true. Now let's quickly see if this works. We're going to call system.out.println ibst.search, and let's search for the value 4. Was this value found in our binary search tree? Sure enough, it was. Now we need to take a look at the remove method for a binary search tree. Much like traversals, this is made a little more complicated based on the tree structure, but also the rules associated with this tree. We want to make sure that every time we add or remove an element from this tree, that we preserve the nature of this tree. All of the data has to be comparable. The left child is always less than the parent. The right child is always greater than the parent. One strategy that we can take to remove an element from a binary search tree is first, we need to find the node with the target value to be removed. Now, if we find that node, then we need to examine the children. If the node that we are going to remove has no children, then what we do is remove that node's reference from its parent. Alternatively, if that node has exactly one child, whether it's left or right, then we replace that node's reference from its parent with the reference to that child. The child replaces the node we are removing. And finally, the most complicated version. If a node has 2 children, then it replaces its value with the smallest value found in its right subtree. Then we must remove the duplicate node from that right subtree. The case where the node has 2 children is arguably one of the most complicated versions. So let's take a look at this as an example. Let's say that we were going to remove the value 2 from this binary search tree. So first thing we have to do is search for that value. If we start from the root, 2 is less than 8, go left. Now we reach here and 2 is equal to 2. We then have to examine how many children this node has. And as you can see, we have both a left and a right child, so this node has 2 children. What we then do is start from the right subtree, trying to find the smallest value. By the property of a binary search tree, we know if we keep going left until we cannot go left anymore, then we have found the smallest value. So starting from that right subtree, we immediately go left. Now when we go left, we've reached a leaf. Now, once we've reached a leaf, we backtrack and we know that this is the smallest element. We then replace the node that we are removing's value with the smallest value in that right subtree, so it becomes this. However, we are not finished, because now we have a duplicate value in our binary search tree and we cannot have that. What we then have to do is remove that duplicate value from the right subtree. Now, starting from here, if we readjust the target to be 4, well, here it is. We found the value. Now we need to repeat the exact same process. We need to remove this node. Let's look at how many children it has. The left and the right child are both null, so in other words, they're both leaves. This means this node has no children. So what we do is replace its reference in its parent with null. Now let's take a look at another example of this. Let's say we're going to remove 8. Well, it's easy to find it because it's the root value. Now we examine the children. It has 2, both a left and a right child. Now this means we start in the right subtree right here. Now we try to find the smallest value in that right subtree. So we simply go left. That's not null. That is null. As we've reached this leaf element and we backtrack, we know that this is the smallest value. We replace that value now. But now, as you can see, we have a duplicate value. In order to preserve the integrity of this binary search tree, we must now call remove on that duplicate value. So once again, starting from the right subtree, we start searching for that value. 10 is less than 12. Go left. Now we found the value. We examine this node's children, and it has no children. So then we replace this reference with null. And finally, we have the binary search tree after we've removed the element 8. And notice, by picking the smallest value in the right subtree, we're able to preserve the structure of this tree. In other words, this value used to be 8, and before everything to the left of it was less than 8, everything to the right of it was greater than 8. When we replace that value with 10, well, everything to the left of this 10 is still less than 10, and everything to the right is greater than 10. Now, let's take a look at how to implement the remove method for a binary search tree. Let's go ahead and start. First, we're going to begin with public void remove, and we're looking for TA data, that target value. Now, just like before, we're going to define a recursive method that's going to be called from this remove. Over here, we're going to create a private node remove, passing in node a node and TA data. Then establishing this, we assign the root value equals to remove starting from the root and the data. Now this would update the root's reference if that root was removed. Now what we need to do is find this data. We got to find the node that contains this information. Now keep in mind, there is a way that we can integrate the method search into this. But in order to keep this simple, let's just write search for this version of remove. So we got to find the node. If we pass in a node, and that was equal to null, that means we reached a leaf. This means we simply need to return null because the value that we were searching for was never found. Now otherwise, if adata.compare to a node.data was less than 0, And as we know, this means this data was less than the node's data. We have to go left. We reassign a node.leftChild is equal to remove a node.leftChild with a data. Now we have to worry about the other direction. Else if a data.compare to a node.data, and this time it was greater than 0, now we know this a data was greater than the node's data, we must go right. A node.rightChild is equal to remove a node.rightChild and a data. Now, if the value wasn't less than or greater than, then we found the value. Once we have found the value, we have to examine how many children that node has. So for instance, if a node.rightChild was equal to null, now this could be the case where the left child does exist, or also the left child could be null. In either case, we return a node.leftChild. This one if statement takes care of 1.5 of the cases. If this left child didn't exist, it's going to return null, which is going to replace that reference. However, if this left child did exist, then we have exactly one child, and we replace it with the left child. However, else if a node.leftChild was equal to null, then we need to return a node.rightChild. This takes care of the other part of that case. Now, if we've reached right here, we know that right child is not null, because if it was, this would have halted here. So now we know the right child is not null. So if the left child is null, that means we had exactly one child, and in this case, it was the right child, so we return that reference. Now, if we haven't returned so far, this means that we have two children, that both the right and the left child were not null. What we need to do is, starting from the right subtree, starting from the right child, find the smallest value in that right subtree. There's a number of ways we could do this, but I'm going to separate this into a different method. To do, find smallest. I'm going to separate this out into a private node, find minimum in tree, node a node. And we're just going to do this recursively. If a node is equal to null, then we need to return null. However, if a node.leftChild was equal to null, this means that the node that we passed in here was not null, and its left child was null. This indicates that this node is the smallest. Return the reference a node. Yet, if that's not true, then we need to return find minimum in tree starting from a node.leftChild. Now, going back to our remove method, what we need to do then is establish a temporary node and assign that to find the minimum in the tree starting from the node that we're going to remove, a node, but starting from its right child. This finds the node that has the smallest value in this node's right subtree. Now we replace a node.data is the temp.data. So now once we're right here, we've replaced the data that used to be here with the smallest value in that right subtree. But the issue is we now have a duplicate node. We have to remove it. In order to do this, we call anode.writeChild is equal to remove anode.writeChild, starting from that right subtree. But this time, instead of looking for a data, the initial value that we're removing, we need to make sure that we remove the duplicate data here. So we call remove this time on temp.data. Now, after we've done that, we return the reference a node. And this allows us to backtrack to the parent's node and then reassign whatever the child's value may be. Let's go ahead and test this out. First, let's call ibst.remove, and let's say we're going to remove the value 4. I'm then going to use ibst.print in order to see if the value 4 was removed. And sure enough, it was. Now let's try to remove the root value 8. ibst.remove 8. Then we call ibst.print in order, and let's see if this works. Oh, sure enough, it did. Now let's look at the complexity of these different operations in relation to the binary search tree. In order to examine this, we have to understand that the complexity of all of these operations, add, remove, search, depend on the structure of the tree. There's two main ways that we can look at these trees. Either they can be balanced trees or unbalanced trees. For a balanced tree, going from the root to any leaf, there are at most log base 2 of n edges reaching it. Now, on the other hand, we can see that this tree is very much unbalanced. So an unbalanced tree has at least one path from the root to a leaf that is more than log base 2 of n edges. So now, looking at the operations add, search, and removed, if this is an unbalanced tree, then adding a new element can take big O of n. So let's look at it this way. Let's say we're going to add the element 17 to this structure. In order to do that, we have to traverse 1, 2, 3, 4, 5, 6, 7 edges before we can add it here. If we had n nodes and it was structured like this, it would take n edges before we could reach that null element. Same thing for search. If we were searching for a value that didn't exist here, like for instance 17, we would have to go through 1, 2, 3, 4, 5, 6, 7 edges before we can confirm that. And if this tree had n edges and was structured in this way, it would take n edges in order to confirm that that value was not there. Remove happens in a very similar way. In order to find the element that we're removing, or in this case, if we're trying to remove something that isn't even there, we have to traverse n edges before we can confirm that. For an unbalanced tree, you really don't get very good complexity values. And in fact, this looks more like a linked list than it does a tree. On the other hand, if we can confirm that the tree is balanced, then it only takes log base 2 of n operations in order to add something. So with our example where we were adding 17, we have to traverse 1, 2, 3 edges before adding it. Now for searching for something, same idea. Log base 2 of n operations to find something. And same thing for remove. Log base 2 of n operations to remove an element from a tree. So this means if we are creating a binary search tree and we can ensure that it always stays balanced, then we get all of these various performance gains. Adding, searching, and removing require less operations in a balanced tree versus an unbalanced tree. So then, how can we ensure that our trees remain balanced? The type of tree that we developed is unbalanced. And in fact, if we were to add the elements 1, 2, 4, 8, 10, 12, and 16 in that order, we would get a tree that looks exactly like this. What we can do is introduce an idea called self-balancing trees. And what these do is you change references until that tree is balanced. And this can be based on criteria like the height of a node or a node's color. In any event, self-balancing trees use what's called rotations in order to balance the structure. There are two types, a left and a right rotation. So like for instance, if we were rotating the value A to the right, as you can see here, it basically moves in this direction to form this. Now alternatively, if we're doing a left rotation on A, then it would end up looking like this. Now there are two popular self-balancing trees, one called AVL and one called the red and black tree. Both of these use these types of rotations. The only difference is an AVL tree bases its balancing on the height of each one of the nodes, and it uses a balance factor in order to determine whether or not that node is balanced. Another way that we can approach it is if we start assigning color values to the node, more specifically the colors red and black. Binary search trees are excellent data structures to store sorted information and quickly search that information out of it. And they have the best performance if we can ensure that these trees are balanced. Now with all of that being said, I'll see you next time.